The intricate, empirical logic of the deep jungle floor translates directly into the precisely calibrated glassware of a modern laboratory. In the dense forests of Western Java, the Baduy tribe operates under strict traditional protocols, completely rejecting the use of synthetic chemicals in their environment. Maintaining these terraced paddies requires a rigorous, systematic defense against the surrounding ecosystem. To repel pests without relying on industrial poisons, the Baduy deploy a highly specific botanical formulation derived from the plants growing immediately around their fields. Securing an agricultural yield in a dense tropical ecosystem requires empirical, optimizable engineering, systems that modern researchers are now systematically reverse engineering. The baseline Baduy protocol starts with a mechanical breakdown, using a traditional stone mortar to manually crush the thick rinds of local pomelo fruit. To extract the active compounds from that pulverized rind, they introduce a precise biological solvent, one-day-old fermented sugar palm juice. The target they are extracting from these pomelo peels is a highly potent specific molecule known as d-limonene. By isolating the exact chemical goals of this stone mortar extraction, modern engineers can adapt the process for the laboratory, swapping the mortar for a conventional kitchen microwave. Analyzing this ethnochemistry provides a biochemical roadmap, allowing us to map the exact mechanisms of traditional practices to design modern, sustainable extraction protocols that outperform conventional lab standards. Stepping down from the physical fruit to the molecular scale, the pomelo peel yields an extraordinarily high concentration of its primary active agent. Over 94% of its essential oil is d-limonene. D-limonene belongs to a class of organic compounds called terpenoids. In an agricultural setting, terpenoids function as highly effective repellents and fumigants. The molecule possesses distinct lipophilic or fat-loving properties, coupled with extreme volatility. This combination allows the compound to breach biological defenses. Because an insect's exoskeleton is lined with a waxy, lipid-based cuticle, the lipophilic d-limonene dissolves straight through that physical barrier, penetrating the insect rapidly. Once inside the host organism, the compound travels directly to the central nervous system, targeting the synaptic gaps between nerve cells. At the synapse, it interferes directly with acetylcholinesterase, a critical enzyme responsible for regulating nerve signal transmission. By physically binding to the receptor sites, d-limonene neutralizes the enzyme. The neural pathways overload and shut down, paralyzing the pest. The Baduy's mechanical crushing of pomelo peels deploys a targeted neurotoxin. Replicating that efficiency in a modern lab requires highly specific chemical engineering. To study and scale the use of phytochemicals like d-limonene, chemists face an engineering bottleneck: how to extract the molecule efficiently without generating widespread environmental damage. For decades, the conventional baseline for this process has been the sock slit extraction apparatus. This method relies heavily on continuous, localized flooding of the sample with volatile organic solvents, frequently using concentrated ethanol. The apparatus forces solvent through an aggressive thermodynamic cycle, boiling the liquid into vapor, condensing it, and raining it back down to strip out compounds. A common alternative is steam distillation. While it avoids organic solvents, it incurs a massive thermodynamic penalty, requiring several hours of continuous, high-wattage heat to separate the oil.
The alternative, inspired by the Baduy protocol, is microwave-assisted extraction, or MAE. This diagram shows the MAE setup, utilizing a 1,000-watt kitchen microwave with a glass funnel and ice condenser. By adding a small beaker of water as a thermal counterbalance, the system regulates temperature perfectly, finishing extraction in 7 minutes without toxic solvents. MAE is faster and mechanically simpler, but to validate it against laboratory standards, its efficiency and safety must be quantified with hard data. Chemists measure the strict environmental sustainability of a process using an analytical tool known as the Green Star metric. This is a holistic assessment that scores methods across multiple principles. We are specifically looking at Principle 5 for safer solvents, Principle 6 for energy efficiency, and Principle 12 for accident prevention. When we map the data from the traditional sock slit method onto the metric, the structural flaws become obvious. This chart shows the sock slit Green Star assessment, scoring a severely contracted area index of just 53.33. It completely fails on Principle 5 due to hazardous organic solvent waste, and collapses at Principle 12 because heating flammable ethanol creates constant fire risks.
Moving to the steam distillation data reveals an improvement in safety, but it introduces a different inefficiency. This chart shows steam distillation achieving a broader total area index of 82.50. However, it fails to reach maximum greenness on Principle 6 because boiling water for several hours degrades its overall energy efficiency rating. Finally, we map the parameters of the ethnochemistry-inspired microwave-assisted extraction. This chart displays the MAE results, filling out a nearly perfect geometrical star. Because the extraction finishes in exactly 7 minutes, it scores the highest energy efficiency and an unmatched green star area index of 88.33. The quantitative data is definitive. MAE is an objectively superior engineering choice, outperforming legacy standards by every measurable metric. This integration is achieved through two-eyed seeing, synthesizing indigenous knowledge with modern STEM to produce sustainable chemistry. Under this framework, cultural practices are hard empirical starting points, tested and optimized to solve modern engineering bottlenecks. By running the resulting pomelo extract through gas chromatography and mass spectrometry, researchers confirmed the exact chemical composition the Baduy have targeted for generations. The GCMS readouts verified a high-yield isolation of d-limonene. The resulting pesticide is completely biodegradable, built from renewable feedstock, and lethal to target insects. Applying rigorous analytical instruments doesn't disprove the traditional philosophy of zero-harm crop management. It provides the exact molecular data proving it works. Validating these compounds in a laboratory is the first step. The next is integrating that validation directly into the STEM curriculum. This chart shows the 5-step pedagogical pipeline used to train chemistry students in evaluating the Baduy extraction method. Students isolate phytochemicals in digital databases, observe the procedure, and perform their own rigorous thermodynamic evaluation using the green star metric. This is the blueprint for next-generation chemical engineering. True innovation requires looking backward at optimized traditional systems just as closely as we look forward. To build a truly sustainable future, modern science must stop treating indigenous practices as folklore and start recognizing them as the highly engineered, rigorously tested baseline for our own survival.